Hello everyone, and this is continuation of our series on electrostatics where we discuss electric potential till last lecture. In this lecture we'll study the next part of electrostatics, which is capacitance, right? Capacitance. So before dealing what is capacitance, let's understand what is a capacitor, right? What is a capacitor? So capacitor is basically a system of conductor, right? It is a system of conductor separated by some insulator, right? So let's say this is a conductor. This can be a conductor. This can be a conductor, and these two are separated by some insulator in between. So this is an insulator, or this is also called as dielectric, right? And this is conductor. Let's say this is conductor 1 and this is conductor 2, right? So when a system is placed like this system is called capacitor, right? Now, before dealing what is capacitance, first property of this capacitor is this is used to store charges, right? This is used to store charges. And now how can it store charge, right? Okay, let's say if I connect this system of conductors to a battery, right? To a battery. If I connect this system of conductors to a battery, what will happen? The battery has two terminals, right? This is symbol of a battery. One long terminal is the positive terminal and the short terminal is the negative terminal. So when this capacitor is connected to this battery, the plus charges will flow through this positive terminal of battery and it will deposit on one plate or one surface of this conductor. The negative charge will flow from negative end of the battery and it will merge on the other plate of the capacitor. Now you see this capacitor is now charged capacitor, right? Until this potential becomes equal to the potential between these two plates, this will keep on charging. But once it attains this particular potential, means the potential of this battery, let's say v is the potential of the battery, and if it attains that much amount of potential, it will stop charging at after that point, right? And now it is charged capacitor, right? Charged capacitor means now if I remove this battery, let's say if I remove this battery, now this capacitor is a charge capacitor, right? So it has a potential in between the plates. Now before there was no potential when there was no charge. Now it has a potential difference in between the plates, right? And it has a electric field in between plates, right? So whenever there is a potential difference, there is a electric field, right? So there is a electric field in between the plates, right? So now equal amount of charge is distributed on the positive and negative plate, right? Let's say this plate has positive plate, this is the negative plate. So if this has got plus q charge, this has got minus q charge, the net potential is v and it has got electric field E, right? Now let's define a term, right? So let's say this is a capacitor, right? Two conductor. So before doing that, let's say representation of a capacitor. Representation of a capacitor, right? So a capacitor is represented like this, like two parallel lines. This is the representation of a capacitor, right? So a capacitor is represented like two parallel lines of equal height, right? It's not like battery. Don't misunderstand it with a battery, right? So this is a representation of a capacitor, or sometimes it is also represented like this with a arrow mark. This basically means this is a variable capacitor and this is a fixed capacitor, right? So we will discuss later on what is variable and fixed capacitor, right? Okay. Now we discuss that if we have a capacitor having charges, sorry, this will be negative charge. So this has negative charge and this has positive charge, right? So let's say plus q is the charge and minus q is the charge on the negative plate, right? And if I am applying potential v to this capacitor, right? So now charge accumulated on the plate of a capacitor is proportional to the potential difference, right? I'm talking about the potential difference, not potential of one plate, right? So charge accumulated. So if let's say if this plate has potential V1 and this has potential V2, I'm talking about V1 minus V2, which is this potential difference V, right? Or this is also usually called as potential, normal potential, right? So charge accumulated. Now again, I'm not talking about the net charge. You see, net charge is 0, plus q minus q is 0. So I'm talking about charge on one particular plate, right? So charge accumulated on the plate of capacitor is directly proportional to the potential applied or potential difference, right? And how did we create this potential difference? By connecting some battery or any other source, right? Now if I remove this proportionality, this q is nothing but q equal to c into v, right? So c, this constant c is called capacitance of a capacitor, right? Capacitance of a capacitor, right? So this capacitance of a capacitor is a constant, and this is the charge storing capacity of a capacitor, right? So if a capacitor has more capacitance, it means it has more charge storing capacity, right? Now if I talk about SI unit of capacitance, so at a SI unit is nothing but it is coulomb per volt, or this usually we use a unit called farad. Farad is a scientist who invented this, so we call farad. Farad is the unit for capacitance, right? So farad is the unit for capacitance, right? Okay. Right. So we discussed capacitor, right? Capacitor is a system of conductors carrying equal and positive charges on their plates, which is separated by a dielectric, right? And it is used to store those charges, right? So capacitor has a property called capacitance. Capacitance is the charge storing capacity of a capacitor, right? So this constant called capacitance, capacitance depends on what? So capacitance only depends on the geometry of capacitor, right? Geometry of capacitor. Geometry means area of capacitor, length of capacitor, distance between the plates, right? So capacitance will depend on the geometry of capacitor, and it will also depend on the nature of insulator or a dielectric, right? So only these two factors will affect the capacitance of a capacitor, right? Apart from this, capacitance will not depend on what voltage I'm applying to it. Capacitance will not depend on what is charge, what is electric field, and things like that. So capacitance will depend only on geometry of capacitor, and it will only depend on the nature of dielectric, right? We will discuss on detail on how it depends on what parameters, right? Now, let's say this is a capacitor, right? This is a capacitor. This is a capacitor. This has plus charge on, this has minus charge, right? Now we discuss the charge accumulated is nothing but C into V, right? Now if I calculate C, I can get Q by V, right? If I calculate C, I'll get what? Q by V, right? Now tell me one thing. Yeah, this is the expression between C, Q and V, right? Now tell me one thing is, if I have a fixed charge, right? I have a fixed charge. So now C and V are inverse relation, right? So for a larger capacitance, I can store same charge with minimum voltage, right? So if for let's say if I need to store plus 5 coulomb charge, right? I have fixed my Q, right? And I need to choose my capacitor, right? So if I choose a capacitor of higher capacitance, I can store this plus 5 coulomb in limited amount of potential, right? And but if I go for capacitor of low capacitance value, then I need to apply high potential to store same amount of charge, right? Clear? Okay. So what is limitation of choosing a capacitors of less capacitance, right? So plates of a capacitor is applied to potential difference, right? Potential difference, right? So this potential difference also create what? Electric field it between the plates, right? This potential difference also create the electric field. Now if potential is very high, this electric field will also be very high. You know, E is nothing but V by X, right? If distance is fixed, right? So if potential is high, electric field will be very high. what is the possibility here? So we have a dielectric or insulator in between, right? Insulator or a dielectric, right? So if electric field is very high, there is a high chance that it will ionize the nearby insulator, right? Since magnitude of field is very high, it will bring out electrons even from a dielectric or insulator, right? And it will ionize the medium in between it, right? And this phenomena is nothing but it is called as dielectric breakdown, right? Dielectric breakdown, right? So there is a dielectric breakdown limit for any capacitor, right? So it is the maximum electric field with which it can withstand this ionization, right? So it is the maximum electric field, maximum magnitude of electric field with which it can withstand the breakdown, right? So as we discussed, now the topic is dielectric breakdown, or dielectric strength basically of a capacitor. Dielectric strength of a capacitor. So we discussed that we have a limitation on maximum potential which we can apply between the plates of a capacitor, right? Because we discussed that plates of capacitor, if we apply a potential difference here, electric field will be created, right? And this electric field, if magnitude of field gets very high, it can ionize the medium here, which is called breakdown. And we are not looking for that dielectric breakdown to happen. It will disrupt our normal functioning, right? So that maximum value of electric field with till which this breakdown will not happen is nothing but dielectric strength of a capacitor, right? Is called as dielectric strength of a capacitor, right? So dielectric strength, like, is not property of a capacitor. So don't misunderstand, it is a property of a capacitor. It is property of this medium which is placed here, right? It is property of this medium, right? Not the property of a capacitor, right? So depending on medium, the value of dielectric strength will be fixed, right? Let's say for air the value is something like 3 into 10 to the power 6 volt per meter, right? So if I apply electric field more than this, and if medium between this is a air, the air will break down, means there will be ionization between the molecules, right? And then there will be external field created because of those ions created, right? And that will disrupt my functioning of normal capacitor, right? So dielectric strength is should so I said it is of a capacitor, but it is we should say that dielectric strength of medium between capacitor, not medium between capacitors, medium between plates, right? So this is dielectric strength of a medium between capacitor plates, right? Right. So next topic for us is parallel plate capacitor, right? Which is a very important topic for all the competitive and board exams as well. Parallel plate capacitor. Parallel plate capacitor. So as the name suggests, these are nothing but two parallel planar sheet of conductors separated by some distance, right? If I can draw diagrammatically, if this is one conductor, so this will also be followed by one more parallel conductor. So this is, and this will be connected to some potential. So this is a kind of parallel plate capacitor, and let's say this has a positive charge and this has a negative charge, right? So this is a parallel plate capacitor. You see there are two parallel conductors, sheet of conductors separated by some distance, right? So if I analytically draw it, right, so there are nothing but there are kind of two plates, right? Let's say this is one plate, this is another plate, right? Two plates, right? These plates have area A, right? The cross sectional area of these plates are A, right? Distance between these plates is nothing but this is small d, right? Distance is d, right? And I'm assuming the medium as air. So permittivity is for air, you know, is permittivity for air is nothing but epsilon naught, right? Which is 8.85 into 10 to the power minus 11, right? This is Coulomb square per Newton meter square. So this is permittivity for air. Now I need to find capacitance of this particular parallel plate, right? Now and we will also understand what that capacitance will depend on, right? So let's say that sigma is the surface charge density of plates, right? Surface charge density of plate of conductor. Let's say both are, we can call it as parallel conductors. Yeah, so sigma is the surface charge density, right? So this particular plate will have positive charges around it. Let's say plus q is the charge on this and minus q is charge on this particular plate. Now this forms a system of capacitor, right? Now before dealing the capacitance, we need to understand what is electric field which is created, right? Let's say if potential v is applied to this, let's say if v is the potential in between these two, right? V is the potential, so what is the electric field in between, right? Okay, so we know that electric field because of any charged sheet of conductor is nothing but it is sigma by 2 epsilon naught. We have studied this, right? It is sigma by 2 epsilon naught, right? Now if I take point left of this first plate, right? If I take a point left of this first plate and if I calculate electric field on this point, because of this plus q, field will be in this direction, and because of minus q it will be in the opposite direction. Net field will cancel out each other. And similar if I go rightmost of the second plate also, and we are only considered about the region between these two parallel plates, right? So we need to calculate what this field is, right? So this field is, right? So because of this plus q, you know, let's say because of this plus q, E1 will be what? Sigma by 2 epsilon naught, right? In this particular direction only, right? And because of this minus q also, let's say E2 will be also sigma by 2 epsilon naught. Again in this direction because it is negative charge. So net field E is nothing but sigma by 2 epsilon naught plus sigma by 2 epsilon naught, which is sigma by epsilon naught, right? This is net field, right? Now I have calculated field, right? Now I know the relation between field and potential as well, right? What is the relation between field and potential? We know, let's say this is equation 1. So we also know that field is nothing but dV by dr, right? Small potential by position, right? Can I write it in this term as V by d? So between these two plates, change in potential is V and distance, change in distance is d. So E is also equal to V by d, right? Clear? Okay. So this is my second equation, right? So both are corresponding to electric field. You see the LHS, right? So what happens is sigma by epsilon naught will be equal to what? V by d. Sigma by epsilon naught is nothing but equal to V by d, right? Now what exactly is this sigma? Sigma is surface charge density, right? So sigma will be what? Q, charge per unit area. This is what sigma is all about. Q is the charge and A is the area of cross section, right? Now if I place this sigma here in this particular expression, can I write it like this? Q by A epsilon naught equal to V by d, right? Now if I take Q by V, it is equal to epsilon naught A by d. Q by V equal to epsilon naught A by d. And what is this term Q by V? Q by V is the ratio, Q by V is the capacitance of capacitor, right? We discussed Q equal to CV. So Q by V is nothing but C, the constant C, which is capacitance of a capacitor, right? So capacitance of a parallel plate capacitor, if C is the capacitance of a parallel plate capacitor, so it will be given by epsilon naught A by D, right? Where A is the area of cross section of plate for one plate only, or plate. D is distance between plates, distance between plates, right? You understood? This is the expression for parallel plate capacitor, right? The capacitance of a parallel plate capacitor. Now see what this capacitance depends on, right? You see epsilon naught for a medium, epsilon naught is a constant value, right? But this capacitance, when we are discussing the capacitance, we talk that it depends on geometry of a capacitor, right? And also the nature of insulator, right? So this capacitance is proportional to the area, right? This capacitance is proportional to the area, and it is also inversely proportional to the distance between the plates. So if I increase the distance between the plates, my capacitance will go down, right? My charge storing capacity of this capacitor will go down, right? But if I keep distance constant and if I increase the area, if I increase the area of my plate, my charge storing capacity or capacitance will increase, right? Okay. So let's assume we discuss for a parallel plate capacitor is C is nothing but epsilon naught A by D, right? So let's say if distance between plates is 1 meter and area of plates is 1 meter square, what is the capacitance? It will be nothing but same value as epsilon naught. So this much farad is my capacitance, right? These two units are general units, which these two values are general values which will be used for capacitor, right? But then also the capacitance which I am getting is in the units of 10 to the power minus 11 farad, right? So this basically tells me that farad is a very big unit of capacitor. If I say 1 farad capacitance, this is a very big unit and not practically used. Generally, if you see capacitors which are used in our fans and regular appliances, the units, if you see, they'll be in microfarad, right? Microfarad, which is 10 to the power minus 6 farad. You will see nanofarad also, which is 10 to the power minus 9 farad. You will see millifarad also, which is 10 to the power minus 3 farad, right? So these are the units which are normally used. Farad is the very big unit of capacitor, right? And that much amount of capacitor and area and length is not practically possible, right? Okay, right. Let's solve one numerical on capacitance of a parallel plate capacitor, right? So the question is, the calculate the capacitance of a parallel plate capacitor having 20 cm cross 27 square plates separated by distance 1 mm, right? So there are two parallel plates which are of square geometry, right? They are separated by 1 mm distance, right? 1 mm is the distance between them. And if you see the length and breadth of this square, this is 20 cm, 20 cm, right? Now we need to find the capacitance of this capacitor, right? You see, only geometrical quantities are given to us here, area and the distance, right? So we know that capacitance we can easily calculate using these geometrical quantities only, because capacitance depend only on the geometrical configurations, right? So now if I recall, the formula for capacitance of a parallel plate capacitor is nothing but epsilon naught A by D, right? A is the area of cross section. So area of cross section of plates is nothing but 20 cross 20 centimeter square, right? If I write in meter square, this is nothing but 400 into 10 to the power minus 4 meter square, right? So nothing but 0.04 meter square, right? Calculation is correct, right? Okay. What about D? D means distance between the plates. So D is given as 1 mm, right? So if I calculate in meter, this is nothing but 10 to the power minus 3 meter, right? Now if I go for and calculate the capacitance, which is nothing but epsilon naught A by D, let's put the values, right? We have all the values here. So it is 8.85 into 10 to the power minus 11. Area is 0.04 or maybe 4 into 10 to the power minus 2, and distance is 10 to the power minus 3. Now what is the value which we are getting here? 35.4 into 10 to the power minus 6 farad, right? 35.4 into 10 to the power minus 6 farad. Is this correct? No, it is not. It is 10 to the power minus 9 farad, right? And if I simplify, this is 3.54 into 10 to the power minus 8 farad. So this much is the capacitance of the capacitor, right? Right. So this is the value of capacitance, which is 3.5. Okay, I think we did a mistake here. Epsilon naught value is 8.85 into 10 to the power minus 12 and not minus 11, right? So it will be minus 12, right? So this is minus, so this will become nothing but minus 11 and this will become minus 10, right? I think this looks good now. Minus 10, minus 14, minus 11, right? And this will become minus 10. Okay, yeah. So this is capacitance of this particular capacitor, right? Now let's move to another topic, right? Let's move to another topic, which, right? Okay, so we discussed that capacitance of a capacitor will depend on two things. It will depend on the geometry of capacitor, right? So which we just saw, that C equal to epsilon naught A by D, right? So A and D are affecting the capacitance, right? So if I say capacitance is proportional to area for a constant distance and it is inversely proportional to distance for a constant area, right? So if area is doubled, capacitance will be doubled, right? So if a capacitor has a capacitance 2 farad, if I double its area, it will become 4 farad, right? And opposite with distance, it is inversely proportional to distance. So if distance is double, capacitance will be halved, right? So things like that. Now next question is how capacitance depends on the insulator which is placed in between that, right? So now next topic will be effect of dielectric on capacitance, right? Effect of dielectric on capacitance, right? So till now what we were discussing, when we discuss any capacitance, we considered the medium between these two plates, which is dielectric, as air, right? And hence we were taking what? We were taking epsilon naught, which is permittivity of air or permittivity of free space, right? So if this medium is air, I can easily go and write c, let's say c naught is the epsilon capacitance, and I can say it is epsilon naught A by D, right? But if there is a dielectric here, right? If there is a dielectric in between plates, right? And let's see how this dielectric will affect the capacitance. Now I'll place a dielectric here, right? So this is a dielectric. It may be anything, any dielectric, might be mica or anything like that. So this dielectric will have a different permittivity, right? This dielectric permittivity will be different from this epsilon naught, right? So now let's say this capacitance will become what? Epsilon A by D, right? Epsilon A by D, right? Now if I take a ratio of these two, right? C by C naught. So if I take a ratio of C by C naught, I can say that C by C naught is nothing but C by C naught is nothing but epsilon by epsilon naught, right? Epsilon by epsilon naught. So this is ratio of permittivity of medium. This medium has a permittivity epsilon and this has epsilon naught. So this is ratio of permittivity of medium to permittivity of air, and this is nothing but relative permittivity, which we discussed even in first chapter, right? And this is also called as dielectric constant, right? Dielectric constant. So so this can be called as dielectric constant or relative permittivity, right? Now if I see C is nothing but K times C naught, right? C has become K times C naught, right? So before my capacitance was C naught, right? Initially when air was the dielectric, the capacitance was C naught. Now after placing a dielectric of permittivity epsilon and dielectric constant K, my capacitance becomes C, right? And now this C is K times of C naught, right? So now my capacitance has increased K times, right? So after inserting a dielectric in between these two plates, I am able to increase my capacitance or charge storing capability by K times, right? Right. So this dielectric is giving me a kind of benefit, right? Now again, when I am able to increase my capacitance, I can store same amount of charge with less potential, right? With less potential, right? Okay. Right. Right, so we discussed capacitance of a parallel plate capacitor. Now let's discuss capacitance of a spherical capacitor. So spherical capacitor are nothing but concentric hollow or solid sphere separated by some distance, right? So since it is concentric, it has a common center, right? But you see there is a gap in between the vicinity of these two, right? And this inside sphere has a charge plus q, outside sphere has a charge minus q, right? Now this has a separation of charge. This is kind of acting as a capacitor, right? And we need to find capacitance of this type of system, right? Let's find what is capacitance of this system, right? So to find capacitance, we need to know what is the electric field or potential in between these two spheres, right? Let's say V is the potential between spheres, right? V is the potential between, let's say, A and B. This is sphere A, sphere B. So potential between A and B, right? And E is the electric field, right? E is the electric field. R1 is the inner radius of this smaller sphere. R2 is the outer radius, which is sphere of the with radius of the outer sphere, right? Okay. Now let's try to find what is capacitance of this particular system, right? So let's first find this electric field, right? Let's take a Gaussian surface. So let's say at a distance r, if I am making a Gaussian surface here, right? So if I calculate electric field at this point P, let's say this point is point P, this will give me electric field between the plates, right? This will give me electric field between the plates, right? Okay. So let's try to do that, right? So electric field. So what is Gauss law? Gauss law says that flux is nothing but charge enclosed by epsilon naught. This is what is Gauss law, right? Now electric field is constant. The area of my Gaussian surface is 4 pi r square, right? This is the area. Charge enclosed is plus q, and epsilon naught will come same as it is. So electric field is plus q by 4 pi epsilon naught r square. Let's say equation 1, right? Now potential between these two, right? We discussed potential is nothing but negative integral of EdR from this limit will be R1 to R2, right? In this case, right? So this is the relation between V and D, right? So if I calculate potential from this particular integral, so this is nothing but integration of q by 4 pi epsilon naught r square dr from R1 to R2, right? So if I take minus here, again minus 1 will come from this integral, minus q by 4 pi epsilon naught will come here. This is 1 by r, and this is R1 to R2, right? So this is q by 4 pi epsilon naught 1 by R2 minus 1 by R1, right? Which is nothing but V, right? So V is equal to q by 4 pi epsilon naught 1 by R2 minus 1 by R1, right? Now what I can do is I can simply say this V by Q, right? Or first find V by Q, right? So V equal to Q by 4 pi epsilon naught R1 minus R2 by R1 R2, right? This is what V is, right? Now V by Q is what? It is 1 by 4 pi epsilon naught R1 minus R2 by R1 R2, right? So V by Q is nothing but 1 by C, 1 by capacitance, because Q by V is C. So if I find C, expression of C, this is 4 pi epsilon naught R1 R2 by R1 minus R2. This is expression of capacitance for a spherical capacitor, right? So you see the capacitance is depending on the radius of these two inner and outer spheres, right? Right. So we discuss capacitance of a parallel plate capacitor. We discuss capacitance of a spherical capacitor. Now let's discuss capacitance of a cylindrical capacitor. Right. Cylindrical capacitor. Capacitor. Right. So let's say this is a kind of cylindrical capacitor. So I have one cylinder which is placed inside, and on top of this I have one more overlapping cylinder, right? So this is a kind of cylindrical capacitor, right? Let's say that inner radius, right? Inner radius of this is R1 and outer radius is R2, right? Inner radius is R1 and outer radius is R2, right? Okay. Now let's say charge on the inner cylinder is nothing but plus q, and outer cylinder it is minus q, right? Outer cylinder it is minus q. Now we need to find what is capacitance of this particular system, right? So let's again, like similar like spherical capacitor, let's draw a Gaussian surface, right? At a distance r, I'll draw a Gaussian surface which will again look like a cylinder. Let's say a very small cylinder I'll draw here, and this Gaussian surface has a height of x, right? And it has radius of r, right? So r is the radius of Gaussian surface and x is length of Gaussian surface, right? Length of Gaussian surface, right? And length of this overall cylinder is L, let's say small l, right? Now we need to find electric field in between these two peripheries of inner and outer cylinder, right? In the gap between these two cylinder, right? Because this is forming a capacitor, right? So we need to find electric field in between. So if I apply Gauss law here, so Gauss law says, so electric field direction, it will be radially outwards, right? So Gauss law says integration EDS is charge enclosed by epsilon naught, right? This is what Gauss law is all about, right? So what is area of this particular cylinder? Area will be nothing but 2 pi r into x. The area of cylinder is 2 pi rl, right? So r is the small small r is the radius and x is the length, and charge is q by epsilon naught, right? So E is q by 2 pi epsilon naught rx, right? This is why what my area is all about, right? Okay, right. So now we have calculated electric field as this is the small part is my Gaussian surface, r is the radius of Gaussian surface, x is the length. I have calculated electric field at the periphery of this Gaussian surface, which is lying between these two plates, I can say, like inner and outer cylinder. So electric field is given by this particular expression, right? But yeah, this charge enclosed by this Gaussian surface, it won't be q. Let's say the charge is q dash, right? Because q is the overall charge, right? Overall charge inside the inner sphere, right? So if length of cylinder is L, right? If length of cylinder is L and it is storing a charge plus q, so this Gaussian surface is having a length of x, how much charge it will store is what we need to find, right? So here the concerned charge density is linear charge density, right? So linear charge density of this particular body is linear charge density is nothing but charge by length. This is q by L, right? So charge inside Gaussian surface, right? Charge inside Gaussian surface. So Gaussian surface has a length x, right? Gaussian surface, which I have indicated as q dash, is q by L into x. Q by L into x, right? Now, if I put this q dash in this expression, right? Let's say expression number 1. So electric field will become 1 by 2 pi epsilon naught Rx into q by L into x, right? So this is q by 2 pi epsilon naught L into R, right? This is my electric field, right? Now, I know potential is integral of electric field over distance, right? And this is from, let's say radius is r1 and r2, which we discussed. So r1 from r2, right? So we need to integrate this quantity minus integration r1 by r2 q by 2 pi epsilon naught lr. So this all is constant, minus q by 2 pi epsilon naught L will come out. This will become ln r from r1 to r2. This is my potential now, right? Okay. So if I calculate, this potential is nothing but this will become V equal to q by 2 pi epsilon naught L ln of r2 by r1, right? This is ln of r2 by r1, right? Now, what is V by q? V by q is 1 by 2 pi epsilon naught ln r2 by r1. V by q is 1 by c. So what is c now? C is 2 pi epsilon naught by ln of r2 by r1, 2 pi epsilon naught L, right? So this is capacitance of a cylindrical capacitor, right? Again, you see the capacitance of a cylindrical capacitor is depending on the length of that capacitor, overall vertical length, and outer radius, inner radius, right? So by this expression you can calculate capacitance of a cylindrical capacitor in farads, right? Clear? Okay, right. So we discussed about standalone capacitors, right? We discussed about 3 type of capacitor: parallel plate capacitor, spherical capacitor, cylindrical capacitor, right? And we also discussed the capacitance depends on the geometry of the configuration and also on the nature of insulator or dielectric, right? Now we will discuss the combination of capacitors, right? Combination of capacitors. So if you see in practical applications, even if you see in phones or anywhere, if you see capacitors or condensers in fan, The capacitors are generally used in combination form, right? Like not one standalone capacitor will be there in any application. You will see a system of capacitors placed, right? So capacitors can be connected in two different ways, right? Which you would have studied in for resistor as well. So one combination is called series combination, right? Series combination, right? And one combination is called parallel combination, right? One combination is called series combination, other is called parallel combination, right? So let's talk what is difference between these two, right? So if I talk about series combination, series combination is nothing but end-to-end combination. You can see this is end-to-end combination, right? The capacitors are connected end-to-end, right? Like one is ending, so the end of first is start for second, and end of second is start for third, and it goes in the same chain, right? So this is what is series combination, right? Parallel combination is combination between 2 points, right? So if I take 2 points and I connect multiple capacitors in between these 2 points, so this combination is called parallel combination, right? So this is a parallel combination. Now what is difference between these two combinations, right? What is difference between these two combinations, right? So if you see parallel combination, if I talk about potential difference, right, which is potential between the capacitors, the potential V is same across all the capacitors, right? So this point, this point, this point, this point are they are all same equipotential points. These are having same potential, right? Again, these 4 points are same. So if all four capacitors are placed between these 2 points A and B, right? So the potential between all the capacitors is nothing but VAB, right? So there is no different potential here, right? But if I talk about series, right, the potential is different. Here it may be V1, here it may be V2, here it may be V3, and here it may be V4. And now net potential, if I say this is V1 plus V2 plus V3 plus V4, right? So the potential is varying over here, but potential is constant in this particular case. Now what about charge, right? Let's not talk about current here, but charge, right? So if I connect this particular system to a battery, right? If I connect this particular system, let's say to a battery, so whatever charge will flow through this capacitor will be same which will flow through this, and which will be same which will flow through this, and which will be same which will flow through this, right? So charge flow will be same in this particular case, right? So if it develops plus q charge, it will also develop plus q, it will also develop plus q, it will also develop plus q, right? So the charge flow is same in this series combination, right? But if I talk about parallel combination, right, so there is a distribution of charge, right? So the charge flow won't be same, right, in case of parallel combination, right? Okay, right. So let's discuss in detail now capacitors in series, right? So now you see, now I have n capacitors connected end to end in series manner over here, right? So now we say that potential is distributed, right? Potential may be different across different capacitors, right? But what common thing we have is the charge, right? So whatever charge is on this particular capacitor will be same which is on this, which is on this, or which is on this. So in series combination, charge is same across, but potential is different, right? Now if I need to find equivalent capacitance, right, like if I need to convert this system to one system, right, so how can I do that, right? Okay, so let's say potential, net potential across this point, let's say this point is A and B, so this is also A and B, and net potential across A and B is V, right? Net potential across A and B is V. And now let's say this potential difference across C1 is V, C2 is V2, V3, and then across Cn is Vn, right? Okay, now if I need to calculate this V based on this CEQ means equivalent capacitance, right? So I know V is nothing but Q by C equivalent in this particular case, right? It is Q by C equivalent, right? Okay, this is charge Q here, this is also same charge Q which is flowing through all, right? Now if I need to calculate V from this particular case, right, so V is V1 plus V2 plus V3 so on till Vn, right? So V1 is nothing but Q by C1, V2 is Q by C2, V3 is Q by C3 until Q by Cn, right? So if this is equation 1 and this is equation 2, both are same, right? Both are correspond to V potential, right? So Q by C equivalent is nothing but Q by C1 plus Q by C2 plus Q by C3 and so on till Q by Cn, right? You see Q is common term, so it will cancel out each other, right? So 1 by C equivalent is 1 by C1 plus 1 by C2 plus 1 by C3 till 1 by Cn, right? So this is the equivalent capacitance, right? So if capacitors are connected in series, the reciprocal of the capacitance, net equivalent capacitance, is equal to sum of reciprocal of individual capacitance, right? And now if you see in series, this equivalent capacitance is actually smaller than all the individual capacitance, right? If you'll analyze, this equivalent capacitance is lesser than all the individual capacitance, right? Let's solve one example, right? Solve one example. So let's say there is a system of capacitors, right? System of capacitors are like this. This is 2 farad, right? And then this is 3 farad between A and B. And I need to find what is the equivalent capacitance, right? So now I have only two capacitors, right? Let's say C1 is 2 farad, C2 is 3 farad, and what is CEQ? C equivalent capacitance is what we need to find, right? We know the expression for series. This is in series, you know. This is end-to-end connection, right? This is in series. So 1 by C equivalent is 1 by C1 plus 1 by C2. So 1 by C equivalent will be equal to 1 by 2 plus 1 by 3, which is equal to 5 by 6. So C equivalent is nothing but 6 by 5, which is 1.2 farad. So see, equivalent capacitance is 1.2 farad, which is smaller than 3, which is smaller than 2 as well, right? So in series, equivalent capacitance is actually lesser than the individual capacitances, right? Okay. Now let's talk about another case, which is parallel combination, right? Parallel combination. Now, now we will talk about capacitors in parallel, right? Capacitors in parallel. Now let's draw a diagram which will connect capacitors in parallel, right? This is one capacitor, another capacitor, third capacitor, and we have something till n capacitors, right? So this is C1, C2, C3 till Cn, right? C1, C2, C3 till Cn, and we need to convert this system to a equivalent kind of system, right? Which is again CEQ, right? Okay. Here if you see, the potential difference between any capacitors here is same. So in parallel we have potential difference or potential as same, right? What is varying is the charge, right? So if this gets Q charge, here charge will distribute. Here it will get Q1, this will get Q2, this will get Q3, and this will get Qn, right? But overall, if you see, addition of this charge will give me what? Will give me Q, right? And if V is the potential between A and B, V is the potential, you can tell me by expression here that Q is nothing but, for this particular system, Q is nothing but C equivalent into V. Let's say equation 1. Q equal to C equivalent to V, right? Let's calculate for this. Q here is summation of all these distributed charges till Qn, right? And you know Q equal to CV. So this is C1V plus C2V till CNV, right? This is equation 2. You see 1 and 2. Q is same in LHS, right? So C equivalent V will be equal to C1V plus C2V till CNV, right? Now if you can cancel out all the V's, you see the equivalent capacitance is actually the algebraic sum of all individual capacitance in parallel. So this is kind of reverse case which we have in resistance, right? In resistance it was opposite for series and parallel, which we have in capacitance, right? So here see, in parallel combination, equivalent capacitance is algebraic sum of all individual capacitance, right? So here in parallel, if you see, the equivalent capacitance is always greater than the individual capacitance, right? It is greater, which is contradictory to the series case, right? Let's solve one example, right? Let's solve one example here. So let's say there is a system which has same which we took in parallel. So 2 farad and 3 farad are connected in parallel, right, in a system. This is a system. Now we need to find what is the net capacitance here, right? What is the net equivalent capacitance? So we know C1 is 2 farad, C2 is 3 farad, right? C equivalent is what we need to find, right? We know this combination is a parallel combination because these two capacitors are between two common points. right? And it has same potential, right? Any charge will come, will distribute, right? So no same charge is going like in series. So this is a parallel combination. So C equivalent will be what? Sum, net algebraic sum. So C1 plus C2, which is 2 plus 3, which is 5. So you know 5 is greater than 2 and 3 both, right? So here net equivalent capacitance is actually greater than both the individual capacitances, right? Okay. Okay, let's solve one more problem here, right? Let's take both series and parallel combination and solve one more problem. Okay. So let's say if system looks like this is 2 farad, this is 3 farad, right? And then let's say this is again 5 farad, and again let's say this is 3 farad, 4 farad, and something like this. So this is a system between A and B, right? This is a system of series and parallel both, right? Now I need to find what is the equivalent capacitance, right? What is equivalent capacitance, right? Now you see here, if I place points, this is A, this is B. Let's say this point is C, this point is D, right? Between A and C, these two are in parallel, right? Between A and C, these two are in parallel, right? Can I simplify this A and C like this? Parallel, you know, it is just sum of these two. So I can say 2 plus 3, which is 5 farad between A and C, right? Let me keep C and B and D same as 5 farad, right? This is 5 farad, right? Again, between D and B, you know, these two are again in parallel, right? So net capacitance is again addition of these two. So this is nothing but 7 farad. Now you can see this combination is now a series combination, right? This combination is a series combination. This is end-to-end connection. I have converted this parallel also to net their equivalent capacitances, and now between A and B I have three capacitors in series, which is 5, 5 and 7, right? Can I calculate the equivalent capacitance now using the series formula? So C1 is 5 farad, C2 is 5 farad, C3 is 7 farad. What is C equivalent, right? And this is connection in series. You know the formula for series is 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3, right? So it will be what? 1 by 5 plus 1 by 5 plus 1 by 7, right? If I take LCM, this is 35, this is 7, this is 7, this is 5, this is 1 by C equivalent. So if I take C equivalent, it is nothing but 35 by 19, which is something like 1 point something, I can say 1.8 farad maybe. So this is the net capacitance of this whole system, which is 1.8 farad, right? So you can solve all these complex problems of series and parallel using this analytical thinking, right? To identify which part of this section or which section of the logics are in parallel or which section are in series, and then you can find the equivalent capacitance, right? Okay. So next class we'll solve numericals on electric potential and also electric capacitance, right? Till then, thanks.